So last time we talked about matrix exponentials, e to the at. I want to do a quick recap and maybe introduce a few new ideas. So what happened? Well, we introduced something called the fundamental matrix, phi of t. And so what you do is you say take x prime equals ax, and you find the solutions. And a full set of solutions, not saying every solution per se, but a complete set of linearly independent solutions from which all other solutions can be built. Now take that and make that into the columns of your matrix, and that's phi. And if you multiply phi of t, phi 0 inverse, the result is what we call e to the at. Now it has some beautiful properties, namely it's a great way to actually solve x prime equals ax, and you can build up solutions very quickly from that. We might say, okay, wait, that doesn't look like exponentials. Why do we call it e to the at? Well, another way to compute e to the at is to think back. We have a series, e to the z. We learned that from calculus 2, advanced calculus. And what we can do is we can plug in a matrix into that series. So we have that e to the a times t. Well, that's I plus ta, t squared over 2 factorial, a squared, t cubed over 3 factorial, a cubed, and so forth. And the beautiful thing is that these are consistent. In other words, if you have a matrix A and you solve x prime equals ax, compute this phi of t, phi 0 inverse, you'll get the same thing as if you plugged that same matrix A into that expression. Wow, cool. Now, one of the things that we were able to do is to say, well, there's some nice things that can happen. If we think about our series here, we saw that if we have the right kind of matrix, then eventually the terms go to 0. Now, there's a term for that in linear algebra. We call those nilpotent. But the important thing is eventually 0 says, oh, you can ignore most of it. So maybe you only have the first 2 or first 3 terms. You only have to look at a piece of it. And so we saw for 2 by 2 matrices, if we had repeated eigenvalues, so our eigenvalues were lambda, lambda, then we could actually compute e to the at very fast. And what is it? It's e to the lambda t times I plus a minus lambda I t. So this gives you a very nice, very quick way to work with repeated eigenvalues. And in some sense, I think it's the preferred way. It's a lot faster, and it's a lot more powerful, because e to the at, what does it have? Well, it's a fundamental matrix, so the columns are solutions. So you can quickly get general form. You can also really quickly get particular solutions. It's just sort of a beautiful way to go about dealing with repeated roots. Now, there's some things we didn't mention, but also make a lot of sense. So, for instance, suppose we have a matrix of all zeros. So if we take e to the all zeros matrix, what should we get? Well, think of the analog of the exponential function. E to the 0 should be 1. Yeah, that's what it is. And you can actually see it, right? Because you can plug in the 0 matrix. What happens is all of the pieces here are the 0 matrix, so the only thing you have is the I. All right, that's pretty nice. You can also say, what's the derivative of e to the at? Now, to find that, we can say, well, what would we like it to be? And we'll just say that's what it is. But let's actually carry it out. Now, you'll see what we'd like it to bring is, you bring the a down in front, e to the at. Because that's what you'd expect, right? That's how the exponential function works. Let's actually carry it out. So we say, well, the derivative of e to the at would be the derivative of this whole thing. Identity plus t times a plus t squared over 2 factorial, a squared plus t cubed over 3 factorial, a cubed, and dot, dot, dot. Now, term by term. Well, in the first place, there's nothing that's varying. It's just the identity matrix. It doesn't have any t. Goes away. Derivative of t times a, Well, again, the only thing that has the t is what's in front, so that leaves us with a. And now, derivative of t squared over 2 factorial is t. And we have an a squared. Derivative of t cubed over 3 factorial, the 3 comes down, and we'll have a t squared. And the 3, it cancels a bit with the 3 factorial, so we're left with 2 factorial, a cubed, dot, dot, dot. Well, now we say, hey, everything has an a. You pull it out. So from here, you'll be left with the identity. Then you'll have t times a plus t squared over 2 factorial, a squared. And you say, wait, that's e to the a t. Aha, beautiful. So this is kind of cool. It says the rules for the exponential function still seem to be working, because they are, it's not just it seems to be, for our case when we plug in a matrix. One more thing which will be helpful. If I want to take the inverse of e to the at, now if you were thinking about this as an exponential function, you'd say, oh, bring the minus in, like e to the minus at. And it's true. This is also the same as e to the power a times negative t. Well, what does that mean? Well, it means if I want to take the inverse of e to the at, I take my expression for e to the at, and everywhere where you see a t, put in a negative t. Simplify, and you're done. So taking inverses is very quick and very, very simple. Now you might say, well, how do you prove it? Well, it can actually be proved directly from this expression, which is to say you take the series for e to the at, take the series for e to the minus at, you multiply them together, and after a lot of bookkeeping, you'll see everything collapses except one term, which is I. And so that shows you that e to the at times e to the minus at is I, which means that it is what we claim. It's the inverse. We'll skip the verification. If you want to do it, great. And there's lots of classes, by the way, which will help you do that. We can suggest it. So, okay, so that's some cool things about matrix exponentials. Some things we've learned, a few new things we've added, and we can actually combine some of these things to do some more fun stuff. Some of it we'll do right now, some of it we'll do next time. So let's do what we're going to do right now. Remember how we said that we can now handle repeated eigenvalues pretty quickly? Wouldn't it be cool if we could do that with other types of eigenvalues which are a challenge, particularly things which were complex? Well, yeah, that would be wonderful. And it turns out we can. All right, so let's see what happens in the case of 2 by 2 matrices when we have complex eigenvalues alpha plus minus beta I. And the claim is we can actually get the e to the at for that very quickly. Okay, so let's step back and say, okay, one of the ways we approached finding e to the at was by using fundamental matrices, x prime equals ax. Now, when we have the case of complex eigenvalues, what does that say about the functions that show up? Well, they look like e to the real part t cosine imaginary part t, so that's e to the alpha t cosine beta t, and similar, e alpha t sine beta t. So we say, oh, those are the functions that show up in phi. Phi 0 inverse is just constants, so when you carry out the multiplication, that says every piece is something that looks like either that or that. Okay, so now we say, great. So let's take our e to the at. We know everything has one of these two terms attached, and we're going to pull it apart. Similar to the way that we've been pulling apart the vectors. Remember how when we had complex eigenvectors, we said, oh, you have the real part plus the imaginary part. Well, we're going to do the same thing, but we're going to say not instead of real and imaginary, we'll say, well, we have the stuff attached to the e to the alpha t cosine beta t, and we have the stuff attached e alpha t sine beta t. So there's two matrices, P and Q. Now, if we could figure out what those matrices are, Success. All right, well, plug in. So plug in t equals 0. We have e to the a times 0 would be e to the 0 cosine 0 p plus e to the 0 sine of 0 q. Now, sine of 0 is 0. Goes away. Cool. What else? Well, e to the 0 and cosine 0 are 1. Okay, so that's 1. Here, a times 0, this is the 0 matrix. And we say, well, wait, e to the 0 matrix is the identity. So we have that the identity is equal to 1 times p. So we say, oh, well, that tells us that p is the identity matrix. So we're halfway there. By just plugging in 0, we've already figured out that part. Okay, so now if we can just figure out that part, we're done. So what do we do? Well, let's take a derivative. So we're going to take a derivative of both sides. And what happens? Well, when we take the derivative of the left-hand side, that's the derivative of e to the at. And what's going to happen is that we're going to have that matrix A is going to fall down and come in front. So taking derivatives, we get a e to the at. That's that derivative. Now, the only place that t shows up are in the functions. P and q are just the numbers. So the derivative of e alpha t cosine beta t, well, that's alpha e to the alpha t cosine beta t, then minus beta e to the alpha t sine beta t, and that's times p, but we know what p is. P is I. And then we're going to add, taking this derivative, alpha e to the alpha t sine beta t, then plus beta e to the alpha t cosine beta t times q. All right, now as we did before, plug in 0. So when we plug in 0, this part will become the identity matrix, just as we did here. Then we'll have that this goes to 1, this goes to 1, goes to 1, goes to 0. And okay, it's easy to plug in to the exponentials and sines, cosines. And okay, so what do we have? Well, we're left with, on the left-hand side, a times the identity, which we simply call a. Then we have alpha times 1 minus beta times 1 times 0, which is alpha. So that's alpha I. Then alpha times 1 times 0, which is 0, plus beta times 1 times q, plus beta q. Well, now we solve for q. So we can subtract the alpha I across. That tells us that beta times q is a subtract alpha I. And then we divide. So q is 1 over beta, a minus alpha I. So we found p, we found q, we found everything. So you plug it in. So you'll see here's p, and then you have q. Don't forget you also have that 1 over beta, and you're done. So now you say, oh, as soon as I have complex eigenvalues, we can now plug it in to this expression for e to the at. We don't even have to find eigenvectors. We don't even have to expand and find our two solutions. And this actually makes it really quick to do things such as solve initial value problems when we have complex eigenvalues. So that's really cool. Isn't it amazing how just a little bit of information can get us a little bit closer, make life simpler? Ah, I think it's the best. So let's try an example. Solve x prime equals 8, 10, minus 5, minus 2 with x of 0 is 6 minus 7. All right, good. Well, what's the first thing we do? First thing we do is find the eigenvalues, and they didn't give us any, So that's okay. We should practice. Practice is good. So we're going to take the determinant. We have 8 minus lambda, 10, minus 5, minus 2, minus lambda. And so as a reminder, this is our A minus lambda I, and where this matrix here is A. All right. Well, just got to go for it. Okay, so this is 8 minus lambda times minus 2 minus lambda, subtract negative 5 times 10. Diagonal, subtract diagonal. That'll give us negative 16 minus 8 lambda plus 2 lambda plus lambda squared, and then plus 50. All right, so all together we get lambda squared minus 6 lambda, and 50 subtract 16 is 34. Okay. Well, what do we do? Well, we try to factor. We try harder. We do not succeed. Okay, so what can we do? Well, we can either do complete the square or quadratic formula. Let's go ahead and do complete the square. I like complete the square. So how does complete the square work? Well, we say, look, let's start with the lambda squared minus 6 lambda. Let's start with the lambda. And then we say, what do we need to add so that we're complete? Well, you take the negative 6 divided by 2, negative 3, square it, 9. So you say, well, we need to add 9. But we have 34. So if I took away 9 from 34, what's left? 25. Okay, cool. So that would become, well, this is lambda minus 3 squared. Move the 25 across, that's negative 25. We can take the square root of both sides, lambda minus 3. Square root of 25 is 5. Because we have a negative, we get an I. And of course, we have two possibilities, plus or minus. And 3 plus minus 5i. All right. Now at this point, you're like, oh no, complex eigenvalues. That was our old thinking. We have new thoughts today. So our new thinking is like, ooh, complex eigenvalues. Well, please and thank you. Because what do we have? We have a formula. So we're not even going to find eigenvectors. So I have the formula over here, what we just worked on. So I'm just going to copy that. And let's see, what do we have? We have that e to the at. I'm just going to copy the formula for right now. Is e to the alpha t cosine of beta t times the identity plus 1 over beta e to the alpha t sine beta t times a minus alpha identity. All right. Now, what do we have? Well, when we talk about our eigenvalues, they're alpha plus minus beta I. So alpha is 3 and beta is 5. So in our case, we say, oh, well, that would be e to the 3t cosine of 5t. And the identity matrix is the 1, 0, 0, 1. 1 over beta, well, that's a 1/5. E to the 3t sine of 5t. All right, I guess I should put in parentheses. And then a minus alpha I. So alpha is 3. So I'm going to come to my a. I'm going to subtract 3 off the diagonal terms. 5, 10, minus 5, minus 5. All right. Well, great. Notice how you have a 1/5 there? So we can even clean this up a little bit further. We have, this is e to the 3t cosine of 5t times 1, 0, 0, 1 plus e to the 3t sine of 5t times 1, 2, minus 1, minus 1. And if we wanted to, we'll go ahead and do it. It's not always advantageous, but we could even put this into one matrix. And what would the matrix look like? It'll be e to the 3t cosine 5t times 1 plus e to the 3t sine of 5t. Okay, so that's the upper left corner. Then we'll have 0. Then we'll have a 2 e to the 3t sine of 5t. In the lower left corner, we'll have 0 minus e to the 3t sine of 5t. And then in the lower right, we'll have e to the 3t cosine of 5t, and then minus e to the 3t sine of 5t. All right. Well, that's the danger of trying to put it all into one line. Now, are we done? Well, we found e to the at, which, by the way, tells us we have solutions that this column here, this is our x1, and this column here, squeezed on the side of the page, is x2. So we have our two solutions, so we can find all solutions by some constant x1 plus some constant x2. But we're after a particular solution. Now, here's the nice thing. When we're after a particular solution, we know that the way we can find it is to say, hey, we're really looking for x is e to the at times the initial value, x0. So here's our idea. I'm going to use this version of e to the at, and I'm going to multiply 6 minus 7. Now, I'm going to do it to both pieces individually. So when we have that, what will we get? Well, we'll have the identity times 6 negative 7. Now remember, the identity acts like 1. So whenever I multiply something times 1, I get that something. So we'll have that e to the 3t cosine of 5t 6 negative 7 plus e to the 3t sine of 5t. Now, okay, multiply 1, 2, minus 1 times 6 minus 7. So we're going to get 6 minus 14. 6 subtract 14 is negative 8. And then we'll have minus 6 plus 7. Okay, minus 6 plus 7 is 1. So putting it all together into one vector, we'll get 6 e to the 3t cosine 5t subtract 8 e to the 3t sine 5t. All right, that's the top term. And then we'll get minus 7 e to the 3t cosine of 5t and plus 1. So plus e to the 3t sine 5t, and we're done. That seems a lot easier than what we were doing before. And then you might say, but wow, you filled up a page. Yeah, but look how much of it was like finding the eigenvalues. And after we found the eigenvalues, it was like pretty quick. So in some sense, now once you have a good tool, it makes life a lot more fun. And so a lot of math is saying, okay, can we make better tools? And if you ever wonder, am I a mathematician? The question is, are you a problem solver? Are you trying to make life easier on yourself? That sounds like a mathematician. All right, cool. Let's now turn onto a new topic. So our goal for the rest of today is to talk about non-homogeneous or non-homogeneous ODE systems. Now, what do we mean by that? Well, that means that we have our differential equation, x prime equals ax plus other stuff, this f of t. Now, why do we call it non-homogeneous? Well, because this has nothing attached to x. It's sort of extra stuff. So it's like, extra stuff. Now, when we encountered non-homogeneous equations before, we came up with two ways to approach it. One way was if the extra parts were nice, we said method of undetermined coefficients. The other way to said, like, well, even if the extra part isn't nice, we can do something called variation of parameters and really, bring out a hammer. We're still going to have both ways. So today, we're going to talk about undetermined coefficients. Next time, next time's going to be good. Variation of parameters. So make sure you come back for that one. So what's today? Undetermined coefficients. Well, it's going to be the same thought process that we had back before. So what was our thought process? Let's remind ourselves. So we were talking about we had a constant coefficient, linear system, sorry, not linear system, linear equation on the left-hand side. And then the right-hand side, over there, we had nice pieces. We said, okay, what we'll do is we'll make a list. Now, when we said nice pieces, there are things that look like exponentials, functions, or maybe we had sines and cosines in exponentials, or maybe powers of t involved. And we said, okay, great. These are the kinds of things that show up as solutions. That's still the case. So we say, okay, what goes on? Well, we channel our making a list. So that's our goal. We're making a list, checking it twice, right? That's the song. We're going to find out which functions are nice to include in our form so that we get the right answer. All right, so how do we go about making our list? Well, the first thing to do is you say, okay, which functions are involved in our f of t? All right, now emphasis on functions. So which functions are showing up? And to help us, the first thing you should do, and I strongly encourage it, is you should pull f of t apart. And when I say pull f of t apart, I mean by the functions that are involved. So you say, okay, well, if I see multiple functions, I'll be like, okay, I'm going to grab everything which has an e to t, that becomes its own part. Everything with a t, that becomes its own part, and so forth and so on. And so that just says, okay, which functions are there? And now that you've identified the functions, that goes into your list. And we start. All right, so are there powers of t? And if there are, then make sure we have the lower powers. So that's the first thing we check on our list. So if we don't have them automatically, we add them. Do we have sine or cosine terms? Well, if you do, make sure they come in pairs. So in other words, if you see a sine of 2t, there's also got to be a cosine 2t. So all right, great. And the last thing is you might say, oh, the bump, Steve, right? Yes. Now, here's the thing you have to be careful about. So, if there's overlap with xc, well, we're going to bump up, but, okay, I want to be really careful here. So, bump up the functions, but, and, all right, I want to make sure we make the but clear. But, all right, so we're going to make that but a different color. Don't take away any old function, which I'll call the smaller parts. We'll illustrate what we mean here. All right, so what it says here, when we bump, make sure you take it all the way down. And also when you bump, things can get weird. That's why you have to be careful. And it's just because of the nature of the problems of systems. So you have to be flexible. And all right, so the good news is we've done it once. We can do it again. So we really want to be experiencing a lot of deja vu. And so try to channel that, like find your inner deja vu. It's like, I know I've done this before. Because you have. Okay, embrace that and do it again. So here's an example to help us get going. We're asked to give the form for xp. So the good news is we don't have to solve for xp. And when we see that, we're like, good. So we don't have to solve for it. And now we have what? X prime equals matrix X. So this part, that's our A. So it's like, okay, we have our AX, and then we have our f of t. So there's our f of t. So we want to do a couple of things. First off, we need to say, all right, we need to pull apart f of t. And we're also going to look at what happens when we look at x prime equals ax, because that's going to play a role as well. Okay, so maybe let's do the x prime equals ax. So we can call that our complementary solution. And complementary solution. So we take x prime equals our 4, 2, 3, minus 1x. We find our eigenvalues, 4 minus lambda, 2, 3, minus 1 minus lambda. All right, and so if you ever feel like, wow, we do this a lot. Well, yeah, we do this a lot, but it's because it's an important step. And when you're solving problems that involve eigenvalues, well, you got to go through and figure out what they are. And so it takes time. All right, so taking the determinant of a minus lambda I gets us to lambda squared minus 3 lambda minus 10. Like, wow, good news, factors. And it does. So that's factors as lambda minus 5, lambda plus 2. And you can check. Lambda squared, good news. Then 2 lambda minus 5 lambda, minus 3 lambda, and minus 10. All right, so that says our eigenvalues are 5 and negative 2. Nice. All right, so now that we have our eigenvalues, we have our eigenvectors as well. Now, what are our eigenvectors? Now, I'll pause here and say, technically, you don't really need to worry about the eigenvectors when you're trying to find the form for xp. We'll go ahead and do it now, just out of habit, but we're going to point something out. When we care about the overlap, it's the particular functions aren't important explicitly, right? We don't explicitly need the right vectors. We need the right functions. But out of habit, we have momentum. We're just going to keep going. So we have, all right, for lambda equals 5, we subtract 5 off the diagonal. That would be minus 1, 2, 3, minus 6 times something should give us 0, 0. And we think about it for a second and say, hey, 2, 1 works. Great. So that's one of our eigenvalue pairs. What about lambda equals minus 2? Well, for that, we would have subtract minus 2. For subtract minus 2, it's really like we're adding 2. 6, 2, and then we'll have 3, 1. And we say something times that gets us to 0, 0. And we're like, what could do that? Well, one thing that does that is 1 and minus 3. Right? You can check, right? 6 minus 6, 3 minus 3. And so we have that our xc looks like e to the eigenvalue t times 2, 1 plus e to the eigenvalue t. Oh, sorry, I forgot some constant a, some constant b. All right, e to the eigenvalue t times 1, negative 3. All right, but in terms of what's important, when we come back to look at this, I don't really care, as I said, about the eigenvector. It's the functions, the e to the 5t, the e to the minus 2t. That's what's important. All right, good. Now, pull apart f of t. So we start by saying, which functions do we see? And, Well, there's a lot of functions. We see there's a t. So okay, so here our f of t looks like t. We say, what do we have? We have a 3 upstairs and a minus 2t downstairs. So it'll be t times 3 minus 2. All right, that accounts for those terms. We have constant. Okay, so we can think of that as just the 1. And we have the 5 downstairs. There's no constant term upstairs. That's okay. That just means we put 0. All right, see how we're pulling things apart? What else do we have? Well, we have t squared e to the 5t. Okay, so that's t squared e to the 5t. We have one of them upstairs, but nothing downstairs. Be careful. These are different functions because they have different powers of t. So we have to treat them separately. And then we might have to move over a little bit to get enough space. Let's do our t e to the 5t. We have no terms like that upstairs, but we have 7 downstairs. And then we have sine t. And we have one of those upstairs, none of them downstairs. Okay, so there's our f of t. So when we start talking about our function, f of t, and how we grow our list, well, we're looking for what functions are involved. We have t, 1, t squared e to the 5t, t e to the 5t, and sine of t. So that's already, we have 5 functions on our list. Okay, good. So here's our list. And we have, I'll put t in 1. I'll put our t squared e to the 5t and t e to the 5t. And we'll put our sine t. All right. Now, after you make your initial list using f of t, you go through the process. Does anything have a power of t? Yes. If it does, make sure we have lower powers. Okay. So we're okay here because t has a lower power of 1 already. T squared e to the 5t, a lower power is t e to the 5t. A lower power of that would be 1 e to the 5t, not on our list, so we add it. There's no t on the outside. All right, next, sines, cosines. No sine cosines, no sines cosines. I see a sine. I better add in my cosine. Okay, cool. Now, finally, do we have any overlap? We do. Now, the overlap is the function part. So we have e to the 5t and e to the minus 2t. E to the minus 2t, no problems. E to the 5t, there's problems. We've got to fix that. And so, since we see an e to the 5t here, we say, okay, what we'll do is we're going to be adding something else. So because there's an overlap of 1, we're going to add one more. So it's actually coming up here. Now, we don't get rid of this one. See, that's the difference here. We don't get rid of the e to the 5t. You still keep it. Now, does it make a lot of difference now? Probably not. However, things get more interesting the higher up we go. We're focusing on 2x2s, and 2x2 is really special. 3x3, you start getting some room for flexibility. So don't read too much into what's been happening with examples that you're going to encounter, because things get weirder as you go higher up. So for now, just remember, you keep things. So what does that mean? That means we have 1, 2, 3, 4, 5, 6, 7, 8 functions. So for each function, that's going to become a piece of our guess. And what you do is, I'll go up the list here. You take the function times some unknown vector. So, okay, I'll use a and b. Then you go to your next function, t, some unknown vector, c, d. All right, now keep moving. E to the 5t. I'm going to skip over the letter e, so f, g. T times e to the 5t. Well, h, and I'll skip over I because that means something to us, j. T squared e to the 5t. All right, k, l. T cubed e to the 5t. And m, n. And, okay, we're in our last group here, plus cosine t. And then skip over O, because that looks too much like 0. PQ, and plus sine of t rs. And there is our xp. So what we have is a collection of unknown vectors, right? So previously it was undetermined coefficients, now it's undetermined vectors. But if you just remember, it's like, oh, make your list. The list making process is still super similar. And once you understand, it's like, okay, make a list. Each thing on my final list gets attached to a vector, and then I have to figure out what each part of that vector is. Then it's not so bad, other than it can look daunting. When we actually ask you to solve, it will not be this bad. But we just want to get the practice of list making done here. So that's why it looks pretty bad right now. All right, we should probably do some more. So let's go for it. More work, more examples. So in this example, we're asked to find the general form for solutions to x prime equals 3 minus 1, 1x plus 3e to the t, 2e to the t. Okay, so general form says we got to find everything. All right, well, first thing is homogeneous part. So when you have non-homogeneous, the first thing is homogeneous. Got to work that through. All right, so we start working that through. All right, so we're after our eigenvalues. 3 minus lambda minus 1, 1 minus lambda. And we take our determinant here. So this is our a minus lambda I. And we just work this through. And, you know, after you do this a few times, it becomes pretty automatic, which is not a bad thing. Of course, just because it's automatic, be careful, because when you're not paying attention, mistakes can happen. So what do we have? We have lambda squared minus 4 lambda plus 4, which is lambda minus 2 squared. Oh, repeated eigenvalues. Okay, cool. That's actually not a bad thing for us. We kind of like repeated eigenvalues. So we're like, noise. All right, so what to do when you have repeated eigenvalues? Well, use matrix exponentials. You say, okay, so our matrix exponential, we have our e to the at is going to be e to the lambda t times the identity matrix plus a minus lambda I times t. So that's a formula we know. So in our case, we get e to the 2t, 1, 0, 0, 1, plus, okay, subtract 2. We're going to get 1 minus 1 and 1 minus 1 times t, which is e to the 2t, 1 plus t minus t, t, and 1 minus t. All right, now from this, we can get our solutions. So how do we do it? Well, the first column will be our first solution. So x1 is e to the 2t. Don't forget the part in front. 1 plus t, t. The second column is our second solution. So x2 is e to the 2t. Again, don't forget the part in front, times minus t, 1 minus t. All right, good. So we have our xc, right? It's this function times some constant plus this function times some constant. Life is good. Now let's move on to xp. We're going to do method of undetermined coefficients because that's the only thing we've learned. But we're also going to do it because we say, hey, that function is nice. And undetermined coefficients, the rule of thumb is it works great when your functions are nice. So we say, okay, what do we have? Well, our f of t, really there's just a single function involved. it's e to the t, 3, 2. So we make our list, all right? And so we start by saying, well, we have the function e to the t. And we say, okay, do we have anything with the t out in front? Nope. Great. Any sines, cosines? Nope. Great. Any overlap? Nope. Because it's e to the t versus e to the 2t. Great. So our list, our final list, is very short. It's e to the t. Nice. Okay. So since we have our list is e to the t, that says our particular solution looks like some unknown. We'll call it a, b, and then e to the t. So the question remains, how do we find the right vector? You know, undetermined coefficients, undetermined vectors. How do you find a, b? Well, it's a solution. So what do you do when you have a solution? You verify. You plug it in. And so you say, okay, so let's take the derivative. The derivative of AB, vector AB times e to the t, well, that'll be AB e to the t. Okay, so keeping track of what we're doing, this part right here, that's our x prime. All right, so this should be equal to 3 minus 1, 1, 1 times AB e to the t plus, of course, 3, 2, and I can pull out that e to the t out of there. And so we have our matrix A, we'll call this xp prime. Here's our A, here's our xp, here's our f of t. Now, since e to the t shows up everywhere, what can you do? You can knock it out. All right, so we do that. Say, farewell, e to the t. Well, we really divide out by e to the t. And let's go ahead and clean this up a little bit. And so, all right, we still have our a, b. Do your multiplication, 3a minus b, and then a plus b. And then plus 3, 2. And at this point, we can read on the top, we can read on the bottom. So a equals 3a minus b plus 3, and then b equals a plus b plus 2. Now, one of these equations is pretty easy to solve because, well, when you rearrange, what do we have? We can move things around. So, for instance, this equation, it tells us if we move the 3a minus b across, minus 2a plus b equals 3. And if we move the a plus b across, we get that minus a equals 2. Well, okay. A equals negative 2. That was pretty quick. And then if a equals negative 2 times negative 2 is 4. So 4 plus b equals 3. Oh, that says b is negative 1. So our particular solution, we can now say, is minus 2, because a is minus 2, minus 1 e to the t. And if you want to, you could pull out a minus sign. So this is minus 2, 1 e to the t. All right, so we're now ready to write our final answer, because we were after the general form. So our general form, x looks like xc plus xp. So we're going to have some constant, all right, c, e to the 2t, 1 plus t, t, some other constant d, e to the 2t, minus t, 1 minus t, and then minus, and I'll put the e to the t in the front this time, e to the t, 2, 1. And that's it. That's our general form. Woohoo! Nice. And so, you see the process, not too bad. And you just work it through. Find the complementary part, break your function, make your list, make sure you grow it as needed. Say, okay, what's the form for xp? Plug it in, solve, and put everything together. Deja vu. Same thing that we did before for undetermined coefficients, because it should be deja vu. All right, good. Maybe one more? Maybe? So let's do one more. Find the general form for solutions to x prime equals the matrix for minus 2, 2, 0, x plus this extra piece 0 minus 4t. And we're told the complementary solution, a e to the 2t 1, 1 plus b e to the 2t, 2t plus 1, 2t. In other words, all the work we did finding the complementary solution, we don't have to do. They gave it to us. Nice. Okay, so we're going to jump straight into particular solution. So remember this part right here. This is the non-homogeneous part. That's what we have to focus on right now. So we say, all right, first off, let's pull it apart. So our f of t, it looks like 0 minus 4t, but there's really only one function, which is the function t. So we have t 0 minus 4. So we start making our list. What shows up on our list? The function t. So I always say, all right, good. So we have t. Go through the rules. Do you have a power of t? Oh, we actually do. Make sure you have lower powers. We don't. So we're going to fix that. So we're going to add another function to our list. Sines, cosines, good to go. Any overlap? Well, overlap would, if we had, would be e to the 2t, which we don't. So great. We have two functions on our list. Okay, so now we're going to take our list and we're going to use that to make our guess. So this tells us that the xp, well, it looks like our function, I'll start with the 1, times some unknown vector, since we're already using a and b. Maybe I'll use capital letters. Capital A, capital B, plus the other function, capital C and capital D. So the goal now is to find A, B, C, D. All right, well, for unknowns. Well, what do? Well, we don't have to think about it. Once we have a solution, we verify, plug it in. One of the first things we learned, it's still one of the most useful. Plug it in. Okay, so what happens when we take the derivative here? Well, what happens is the constant stuff goes away. Derivative of t is 1. So we have CD. And as a reminder of what's going on, this part right here, that's our xp prime. All right, this will be equal to, and then we're going to take our 4 minus 2, 2, 0, times our vector a times b plus t, c times d, and then we're going to add that to 0 minus 4t. So we have our A, matrix A, same matrix as before. I'll just copy it down here. Our xp, and here is our 0 minus 4t. Okay, great. Now, well, we keep cleaning it up. And by that I mean we do the multiplication. So, what do we have? Well, 4a minus 2b. And then we'll have 2a plus 0b. So that's 2a. So that's the first piece, plus t, 4c minus 2d. And then we're going to have 2c plus 0d, 2c. And then plus 0 minus 4t. All right. Now, at this stage, we're going to break things, top and bottom. So, we will have the following. Reading along the top, we have that c is equal to 4a minus 2b plus t times 4c minus 2d plus 0. All right, and along the bottom, we'll have that d is equal to 2a plus t times 2c and then minus 4, right? T times 2c, t times minus 4. All right, well, cleaning it up a little bit more, I'm going to move the c and the d across. So this becomes 0 is equal to 4a minus 2b minus c plus t 4c minus 2d. And the bottom equation becomes 0 is 2a minus d plus t times 2c minus 4. All right. Now, how do we actually solve for our numbers, a, b, c, d? Well, the thing is, we really have polynomials. We have number plus t times number equals 0, number plus t times number equals 0. So what we really have is that each of these 4 pieces is an equation. Each of these 4 pieces must be 0. So 2c minus 4 has to equal 0. 2a minus d has to equal 0. 4a minus 2b minus c has to equal 0. 4c minus 2d has to equal 0. Can we make progress in any of these equations? I see 1. 2c minus 4 equals 0. All right, if 2c minus 4 equals 0, what does that tell us about c? It tells us c is 2. We could add 4 and divide by 2. So we say, c is 2. Cool. All right, well now we know c. Well, notice here, this part says 2d is 4c. Or you could say d is 2c. But we know what c is. C is 2. So we get d is 4. Okay, so now we know c and d. Okay, so we say, look, c is 2, d is 4. Great. What else? Well, Well, since we know those terms, we can say, look, d is 2a. So we can say 2a is equal to 4, because d is 4. I say, okay, so what does that tell us? Well, that tells us that a is 2. Great! We're almost done. What don't we know? Well, we don't know b, but we have one more equation. All right, so here we go. 4a. a is 2, so that would be 8 minus 2b, and then minus c would be minus 2 equals 0. Now, if we rearrange that, that says that 2b is equal to 6, or says that b is equal to 3. All right, great. So now we know b, which means we've got our xp. All right, so how do we finish it? Well, we've already got xc because it was given to us. How nice of them to do that for us. They must really like us. I think we're probably one of their favorite students. Okay, all right, so let's put it all together. So we have that x is equal to our xc, a e to the 2t, 1 plus b e to the 2t, 2t plus 1, 2t, then plus our xp, plus, and we can even combine this together, 2 plus 2t, and 3 plus 4t. And we're done. That's it. Woohoo! All right. Well, that's some good exercising that we've done. And so we're ready. If we see any problems like this, we'll know what to do. So on to bigger and better things, and we'll save that for next time.